All right. Hello, everyone. My name is Andrew Hobson. This is my presentation on calorimetry. Let me just get it going real quick. Share my screen. Okay. All right. So my presentation is titled Calorimetry is the bomb.com. Very creative. So first, we're going to start with the introduction. So experimental goals. Like any other experiment, you're going to need a goal you're trying to achieve. In this calorimetry experiment, we're trying to determine the resonance energy of benzene using both experimental and theoretical methods. Additionally, we'll be using a bomb calorimeter to help us calculate the heat of combustion for CDDT and cyclohexane. These values gathered up will also help us calculate an experimental value of the resonance energy of benzene. A little about calorimetry. We use it to measure the amount of heat released or absorbed in a chemical reaction. Bomb calorimeters, as seen in the image on the right, are extremely useful for measuring the combustion reactions in constant volume reactions, which is like the one we did in this experiment. The oxygen bomb used in this experiment will allow us to measure a number of factors, and like the enthalpy of combustion of CDDT and cyclohexane, which, like I said, will eventually get us to calculate the resonance energy of benzene. Well, background and significance. In this experiment, we're using CDDT as intermediate in order to measure the resonance energy of benzene. Testing for the amount of heat released during the reaction shown we were able to achieve our goal. We consider this type of reaction isodemic, which means that the number and types of bonds in the reactants is the same as in the products. So in theory, the heat of combustion of CDDT, as seen in the photo, will equal the sum of the heats of combustion of benzene and cyclohexane, but it's not the case. This method assumes that benzene doesn't have any resonance structures, which we know it does. Resonance occurs when electrons in a molecule are delocalized or flowing freely inside the molecule, allowing for multiple structures to be possible. We're going to use Hess's law, as seen on the right, to work around this hindrance. It's a big picture. Our big picture goal is to understand the resonance energy of benzene through experimental and theoretical methods. Using a bomb calorimeter is our method of doing this. Like I said, hoping that once we understand this value, we can understand how companies and industries use benzene to produce products. So hypotheses. We had two hypotheses for the experiment. We'll start with the first one. The first one states that the heat of combustion for CDDT will be larger than cyclohexane. This is due to a number of carbon atoms in each molecule. However, since the heat of combustion is directly proportional to the number of carbon atoms, we expect that CDDT will be larger. Our other hypothesis states that the method that will work best for finding the resonance energy of benzene will actually be through Hess's law and not Segrist or any other theoretical method that we'll be using. So we're going to move on to theories and methods. We'll be discussing more about the experimental procedure and setup, and a little more about Segrist. So the setup, we're just going to talk about what we're using. For this experiment, we're going to need the oxygen bomb calorimeter, as seen on the right, a basket, a fuse, the fuse wire, that's very important, 1 gram samples of CDDT and cyclohexane, lots of DI water, we're talking multiple liters, an oxygen tank to pressurize the bomb, a calorimetry bucket, one dotted, one not dotted, an ignition unit, and obviously the bomb cal software on the computer that we're going to need to run the experiment. All in all, we actually ended up detonating 3 CDDT bombs and 3 cyclohexane bombs. So the procedure, the actual experiment began with prepping the samples to run. CDT and cyclohexane, to be exact. We needed to fill the sample basket seen on the other slide to about 1 gram of either CDT or cyclohexane. We had to then adjust the 10 centimeter long fuse wire that would help our explosion by touching the sample, but not the bottom of the sample basket. That could really mess things up. Once this is done, we're going to add about 1 milliliter of water to the bottom of the oxygen bomb outer case. Then we place the fuse inside while being extremely careful to make sure that the lid, once we're done, is completely tightened, because if not, it will not explode. We then closed the pressure release valve and vented the bomb twice. Once that was complete, we actually pressurized it again with oxygen to about 30 ATM, placing the bomb then inside a calorimetry bucket. which was either dotted or not dotted. We'll talk about that later. Which we then filled with 2 liters of DI water, connected 2 ignition wire pins on top. We let the stirrer run for about 2 minutes while we got the bomb cal software set up on the computer. And once we ignited the bomb, the software recorded the temperature inside the bomb until it hit about its max temp. Then we waited another 90 seconds before shutting it off. We completed this process for all 6 bombs. So CGRIS. In this experiment, we used a computer software program that's extremely useful for molecular modeling. Here are other 3 molecules of interest, as you can see, benzene, CDDT, and cyclohexane, all from CGRIS. CGRIS actually takes the optimized geometry for each molecule at the PM6 level, which then allows us to find the heat of formation, which we'll discuss later in the presentation. CGRIS is a very good computer program, but it does have its downsides every once in a while. Sometimes it's very hard to use and certain computers can't run it, like mine, so you have to do it on campus. We're gonna move to our results section. So here we had to gather some literature values before we could really begin. We were also tasked with finding the combustion of benzene and the vaporization energy of benzene and cyclohexane, or the enthalpy of benzene and cyclohexane. Using this, I was able to find these values. We'll need these for later data analysis. Using the data given in our experimental handout, we were also able to use the equation below, the bottom right, to calculate the enthalpy of vaporization of CDDT. When we plug the data from the left table into this equation, we actually get a value of 44.37 kilojoules per mole. And then we're able to use the data from the table on the left to obtain the plot on the right, which shows the vaporization of CDDT as it changes. So delta U combustion and delta H combustion was also another thing we had to find for this experiment. To get delta U, we needed to use the equation on the left-hand side on the bottom, which was relatively easy since the C bomb value was actually given to us in the handout. This is what I was talking about with the dot and the not dotted bucket. It changes slightly depending which one you use. That value is given to you. Once you get your delta U, you can plug and chug in the equation on the right, and that's how we get our delta H values. And then we're able to average them as seen on the chart. So here I'm actually going to show you all 6 runs at a time. First cyclohexane and then CDDT. So there's labels on each of these. So our TI represents the time of initial temperature. TA represents the time of the firing of the bomb. TB represents about 60% of the total temp change during the bomb going off. TC actually represents the max time of the bomb. And then TF is like right around 90 seconds or wherever we stopped after the max temp was hit. Here's the same thing for CDDT. Here's the data points from all of these. Like I said, all the 6 runs. Using these values, we're then able to calculate the temperature change in each of the 6 runs. Our largest being in the CDDT second run. That's our largest temperature change. So now resonance via CGRIS, which is our theoretical run or values. Using CGRIS, we're able to find the formation energy of benzene, cyclohexane, and CDDT. These values then allow us to create a theoretical value for the resonance of benzene, which comes up to about 37.4 kilocal per mole, versus our experimental values. So pretty much we're doing the same thing here. Our data actually is now found for tables 1 and 3 earlier in the presentation. Essentially, we're completing the same calculation to find the resonance energy of benzene, but this time we have to convert from kilojoules per mole to kilocal per mole. This result gives us a value that is lower than expected, which is around 8.5 kilocal per mole. Discussion, we're going to talk a little bit more about the results. So what do they really mean? Our results tell us that the resonance energy calculated by CGRIS is actually more accurate than our experimental method. This discrepancy could have been occurred due to the data analysis section error by me, possibly. Overall, now we know the resonance energy of benzene and how to find it experimentally and in theory. The purpose of this experiment was to evaluate the resonance energy of benzene by using both experimental and theoretical methods. As we've already discussed, we use a bomb calorimeter to obtain the combustion or heat of combustion of cyclohexane and CDDT. Using these measurements along with the literature ones we already found earlier from NIST, we're able to find experimental values. So yes, to sum it up, we were able to answer all the questions we set out to investigate. So do we support our initial hypotheses? We know from experimentation that our first hypothesis was actually proven to be correct. The data to back this up can actually be found, I think, in table 3. However, our second hypothesis was not true or not proven correct. The Segrest method seemed to be more accurate and a better method overall than for finding resonance energy of benzene than any other method we used. The relevance of these findings. Well, now that we know and how to find resonance energy theoretically and experimentally, we understand more about benzene overall. And researchers and scientists in the real world use this information every day when they're making certain products like plastics, dyes, synthetic fibers, nylon, and other things that use benzene. So there's a lot of applications of this knowledge. We're able to use bond enthalpy information to determine the resonance energy of benzene actually. Since resonance energy is defined as the difference in energy of the resonance hybrid and the energy of the most stable resonance structure, we're able to determine the standard enthalpy of formation using bond enthalpy of benzene as delta H theoretical. This enthalpy change during the formation of benzene represented by the equation shown on the left. If we know the experimental standard enthalpy of formation of benzene, which we actually do through the experiment, we're then able to calculate the resonance energy with that. Moving on, since our molecule on the left is cyclotetraene, I think, is a benzene ring expanded by an ethylene group. We know that the resonance energy of benzene can then be estimated by comparing this value to the heat of combustion of cyclotetraene by subtracting the ethylene. As shown in the equations in the middle, since cyclotetraene is now unconjugated and contains 4 ethylene groups, its energy of combustion of 3 of these ethylene is now described as H3, as seen on the left, or in the middle, I'm sorry. Therefore, the difference between H1 and H3 represents the resonance energy between a benzene ring. This, of course, takes into account that there's no resonance going on. So we're also tasked with explaining the resonance energy of these structures below. On the farthest right, benzene is aromatic, and therefore we know that its resonance energy is very high. Next up, cyclotetraene, like we just talked about, lower energy than benzene because it's not aromatic, also has a planar structure. Then we have our 2 conjugated chain analogs of C6H8 and C8H10. They're next in line. This is due to their non-cyclic structure, resulting in a much lower resonance energy. Another method that we can use to find ERES of benzene. We can take the heat of hydrogenations. We would take a hypothetical system that has 3 isolated double bonded carbons and then compare the heat of hydrogenation with benzene. This difference between the two can, I'm pretty sure, give us the resonance energy. We're going to wrap it up with some conclusions. So the main takeaway from this experiment is that the Segrest method was actually proven to be more accurate when measuring the resonance energy of benzene. Only our first hypothesis was proven to be correct. Our second one was proven wrong, like I said, because Segrest was more accurate. And the only source of error that I can really think of was probably my calculations during data analysis that could have thrown off the final result. Other than that, there was nothing else. Final acknowledgements. That concludes my presentation on the calorimetry experiment. I'd like to just thank the University of Pittsburgh and the Chem department for allowing me to conduct this experiment. A special thanks to Dr. Wagner, who was in charge of the Chem 1430 labs this semester. Also, this experiment would not have been possible without the help from our 2 wonderful grad TAs, Sydney and Tyler. And lastly, I just want to thank my lab partner, Derek, who I worked with the whole semester and couldn't have done without him. I'm just going to stop my share. All right, thank you so much. I know I ran over by a little bit. Hopefully it doesn't, it's not too much, but all right, thank you.